Today we'll be talking about largest rectangle in histogram. The problem statement is given an array of integer heights. Return the area of the largest rectangle in the histogram. We can see that the integers are a simple array, and this can be visualized in this histogram. There's a few candidate rectangles we can form with this. So for example, you can consider this 2 by 4 rectangle, which has an area of 8. We can also possibly consider this 6 by 1 rectangle, which is of size 6. And finally, we can consider as well this 5 by 2, which is optimally, and our answer, area 10. So the first approach we'll talk about is fairly intuitive. The idea is that for any given bar, what we're going to do is try to expand it to the left and to the right. So for example, with this 5, you can see that we can't really expand to the left and right because the bars around it are smaller. But if we pick a bar like, let's say, this 3, we also can expand to the left, but we can definitely expand it to the right. And in fact, it'll go through multiple columns. So let's just trace this out real quick. So let's try with the first column on the left, which is the column size 1. So that will be our current. But what we're going to do is take a bar. We're going to fill it with 1 height. And let's try to expand it to the left. Well, we can't because it's the first bar. But we are able to expand it all the way to the right. So let's try that. And we're going to expand all the way to the right. And notice here that, we've got a height of size 1 and, width of 5. Great. So now let's try the next column. We're going to take the 3. Similarly, we can't expand to the left, but we can expand all the way to the right. And so we end up with a column of height 3 and a width 3. So it's a result of 9. And then finally, we can do the same for the third column. And again, this one doesn't expand to the left or the right, so we're done. We have a column of height 5 and width 1. And then, of course, you would repeat this again for the remaining columns. Let's briefly talk about the space and time complexity of this problem. So keep in mind that for any given column, let's pick this one, we're going to look to the left and to the right. What this means is that for this first column, we're going to stop here, but we're also going to traverse through here and here and here, which means that we're going to look all the way ahead and we're going to have to take 4 steps to do that. So you can imagine that the worst case for this algorithm, if we've got all bars of height 1, we're going to do the same approach from every column. So for example, if this is a 1, we're going to look left and right a total of 4 times. We're going to traverse every other column. What this means is that for any given column, we are going to possibly hit every other column. And so, in time complexity terminology, that would be an n-squared algorithm. So the benefit of this algorithm, however, is the space complexity, because what we are keeping track of is just the currents and the left and the right. So we're going to be using 3 pointers at any given time. And that's pretty much it. You might need to keep track of something like the best or something like the current height. So in terms of space, it's constant, regardless of the input size.
So in our previous approach, we talked about a way of solving this problem by starting at every column and scanning every other column. And the time complexity for that approach, for the left, right, scan approach, was we had to start at every column. Right, so start here. And then we had to look left and look right at possibly every column. So what that means is for every column inside of this histogram, which is n columns, we had to look at up to another n columns. And this meant our total time complexity was O of n squared. So this is not bad, but let's see if we can do better. So if we're going to do better than this, we have to either reduce the left or the right hand side of this equation. And in terms of looking at the columns, we can't really figure out the rectangles without looking at the actual columns. So what that means is we're going to have to figure out some way to decrease this scan right here to less than O of n. And the way that we can do this is with a core idea, being the nature of the ascending sequence of columns. And what that means is this. So take, for example, 1, 3, 5. Whatever column in this sequence, this ascending sequence, knows is that it cannot expand to the left. Because by definition, if the sequence is ascending, then the column to its left must be shorter. Therefore, you cannot form a rectangle with the column to its left. And it's the same thing for 5. Right? If you try to expand to the left, you can't because the 3 is shorter. And what this means is that when we have an ascending sequence, there actually is an implicit left bound before every single column that cannot be expanded upon. So let's see how this is useful. The structure we're going to use to take advantage of this is going to be a stack. And the rule of the stack is going to be our core idea. We only keep indexes of the ascending sequence inside of the stack. So first goes in 0, and then index 1, and then index 2. Now, when we're at index 3, we have an issue. 3 is less than 5, so it's no longer ascending. So therefore, we must get rid of the 5. So popping this out of the stack, we first measure the area that this column can expand upon. And the way we do it is with two things. First of all, we know the right wall of this column is where the popping started, which is this 3 right here. And the left wall of our expansion is the next element inside of the stack, which is index 1. So knowing this left and right wall, we can do a simple calculation. 1 width times 5 height is area of 5. Okay. So now the 5 is gone, just the 3 is left. But the problem is, since we're doing only ascending, we can't have two 3s inside of the same stack. So this 3 also has to go. Taking it out, right, we do the same thing again. The column that started the popping is index 3, so that's the right wall. And then the left wall, for our current column of 3, it's the next element, so it's this 0 right here. And with the left wall being here, and the right wall being at 3, we do a calculation. 2 times 3, that's an area of 6. Okay. So now, since everything that's greater than 3 has been removed, we can now put it in. Okay, so we keep going. We have a 1. This also doesn't fit the ascending because 3 is greater. So we got to get rid of this 3. 3 goes out. And we do the same measurement. But an interesting thing happens here. The right wall is the one that started the popping. But take a look at this. The left wall is at 0. Which means that we know this 3 can expand until 0 without actually looking at the previous index, the previous, and the previous. All we did was we looked at the next element in the stack, which is an O of 1 operation, instead of O of n. 3 wide, 3 tall, area of 9. So with this implementation, since we managed to reduce the scanning time from O of n into O of 1 with the stack method, our total time complexity is actually O of n. Much better than this O of n squared. Alright, now onto the code. So first, we'll declare two variables here. One being the stack, and then the other one being a variable called best. This is where the result will be. Now, we'll use a for loop to traverse through the array. So you might notice something that's a little bit weird here, which is that instead of the normal less than that we use for array traversal, we actually have a less than or equal to. And the reason for this equal is that there actually is an edge case that needs to be considered, which wasn't included in the high level. And the edge case is this. Sometimes, by the time that we're at the end of the input array, we will still actually have a couple columns instead of a stack that has not yet been popped out yet. However, if we don't pop those out, we can't really measure them. So the solution that I use here is that if we're at the end of the input array, I will create an extra column with 0 height. And what will happen with this 0 height column is that it will cause the remaining columns inside of the stack to all be popped out. And this will cover the edge case. Next, we'll talk about the popping mechanic of the stack. We'll do it with a while loop here. So the while loop will have two conditions. Number one is the stack cannot be empty. If it's empty, we can't pop from it. And the second condition is the rule of our stack, which is that if the element coming in is less than the element that's at the top, then the top must come out. And you'll see that here. So first, we take out the top element. And then we check for its height. Because remember, what we store inside of the stack is actually the index of the columns, not the height. So once we have that, we can look for its left wall. This will help with the width. And the left wall is a little bit tricky. So first, let's talk about the normal case. And the normal case is this. Normally, the left wall is whatever is next inside of the stack. However, there's this lingering +1 here. It might seem kind of like a magic number, and we don't like magic numbers. So why is this here? So take for this example. Say we have two columns that are inside of the stack, and then all of a sudden we have a third one that comes in that initiates the popping. Now, if I take out the 1, what will be the width here? The left wall, we look left, is 0. This is the left. And the right wall is the column that begins the popping, 2. But if we take 2 minus 0, we get a width of 2, even though we only have one column. Now, how do we fix it? It's very simple. Since we know that it will often overshoot by 1, we have to add this +1 here. So instead of 2 minus 0, we have 2 minus 1, which gives the correct width. Next, what is this 0 here? Now, this is another edge case that we have. If the stack is empty, where should the left wall be? Well, let's see. So say I have an ascending sequence, and then all of a sudden a very short column that ends up popping both of these. How far can this column expand? Well, if there's nothing inside of the stack, that probably means the current element is the lowest. Which means when the now lowest column is popped, it can probably span across the whole histogram. So therefore, we'll simply set the left wall as 0 and calculate the width from there. Okay. Now the remaining parts are pretty simple. We take I, which is our right wall, and then we minus the index of the left wall that we got from over here. And then after that, we simply do a test. Between the best and the current rectangle, which one is better? If the current one is better, we'll update best. And that's it. And after all the popping is done, we simply add the current column into the stack.